Okay, today we're going to talk about reviewing radicals, or square roots, and also quadratic formula with real solutions. We have two objectives today. First of all, we want you to be able to rationalize radical expressions and express them in simplest form. And we want you to be able to use the quadratic formula to solve quadratic equations that have real solutions. Okay, if you recall, the set of all real numbers is broken down into two main parts. The first part is called rational numbers. Okay? The second is called irrational numbers. A great many of square roots fall in the irrational category. Okay? And so we want you to be able to work with those types of expressions and be comfortable with them. You should have had a review in geometry last year about radicals, but I've noticed that several people still do not have an adequate grasp on them, and so we are going to review it yet again for part of today's lecture. Remember, if you want to be able to break down square roots, you have to know how to do prime factorization. So say something like 72 would be 8 times 9. Well, 8 is 2 times 4, 9 is 3 times 3, and 4 is 2 times 2. So 72 breaks down into 2 times 2 times 2 times 3 times 3. And remember, there is one and only one prime factorization for every composite number. And composite numbers are numbers that are not prime. Now let's talk about radicals, or square roots, okay? They are typically irrational numbers, provided they do not have factors that can be considered rational. Like the square root of 25 can be broken down into the square root of 5 times 5, which is the square root of 5 squared, which would be 5. Okay, so therefore square root of 25 is not irrational, it is in fact rational. Now, the square root of 30 is slightly different. It breaks down into 2 times 3 times 5. None of these factors have repeating factors. Notice 5 times 5 up here was a repeating factor. The square root of anything squared is itself, and so when we have the square root of 5 times 5, that just becomes 5. Well, we don't have any of these things down here in the square root of 30. And so square root of 30 will just stay the square root of 30. There's no pairs that we can bring out from underneath that radical. Let's look at a few other examples. Square root of 125 breaks down into 5 times 5 times 5. Well, the square root of 5 times 5 is like saying the square root of 25 times the square root of 5. Well, what's the square root of 25? That's just 5. So we're left with 5 square root of 5 for the square root of 125. 54. That breaks down into 6 times 9, which is 2 times 3 and 3 times 3. So we have the square root of 2 times 3 times 3 times 3. And if you look at this as we have a pair of 3's, that would be like saying the square root of 9. And 2 times 3, there are no pairs in there, so that will just remain the square root of 6. Square root of 9 is 3. So we end up with 3 square root of 6 for the square root of 54. Square root of 162. Ends up being the square root of 2 times 81. Well, the square root of 81 is 9. And the square root of 2 is just all by itself. So that simplifies to this 9 square root of 2. Adding and subtracting radicals. Remember, radicals can be added, subtracted, and multiplied as long as they have the same number underneath the radical. This is like when we had exponents and we could add exponents that had the same base. Well, radicals work the same way. Our base in this case is what's under the square root. So 2 square root of 3 plus 5 square root of 3 would be 7 square root of 3. Sometimes we have to simplify our radicals before we can add them. So 3 square root of 12 turns into 3 times the square root of 12, which is, let's see, 4 times 3, which is so 2 times 2 times 3 is all 12. Here we have a pair of 2s, so we end up with 3 times 2 square root of 3, which is 6 square root of 3. And the math behind this is I have 3. Square root of 2 times 2 is like the square root of 4 times the square root of 3. Square root of 4 is 2, so that becomes 3 times 2 times the square root of 3. And that's how we got back up to this point, so we could simplify that. Well, we knew that 3 square root of 12 was really 6 square root of 3, and 2 square root of 125. Remember, square root of 125 was 5 square root of 5 from the last slide. So this ends up being 2 times 5 square root of 5. So this is 6 square root of 3 plus 10 square root of 5. Because these bases are not the same, we can't add them. So this is all that we can do is simplify it a little bit. Subtracting radicals, again, subtraction is addition, just with a different sign. And so 4 square root of 7 minus square root of 7 is 3 square root of 7. And we can work these other ones in much the same way. We just have to simplify them first. So we know that square root of 8 is square root of 4 times 2. Ooh, I see a perfect square, so I'm not going to break it down anymore. That gives me 2 square root of 2 times our 8, which is 16 square root of 2, minus square root of 18 breaks down into square root of 9 times 2, square root of 9 times the square root of 2, which is 3 square root of 2, times our 4, so that gives me 12 square root of 2. Now 16 square root of 2 minus 12 square root of 2 gives me 4 square root of 2. I hope this is making sense. If not, look back a couple times and rewind this. Square root of 125. Again, that breaks down into 25 times 5. What's the square root of 25? 25 times the square root of 5 is just 5 square root of 5. So, and we have that times 3, so that becomes 15 square root of 5. So this is 15 square root of 5. And then we have square root of 72. Well, we knew 72 was 8 times 9, and that's 4 times 2 times 3 times 3, and that's 2 times 2. So we end up with a square root of 2 times 2 times 2 times 3 times 3. So we have a pair of 2's and a pair of 3's we can bring out. So that is 6 square root of 2. Times our 2 gives us minus 12 square root of 2. And we can't subtract those because they do not have the same number under the square root. Multiplying radicals. Here we don't really care. We just apply the distributive property. Numbers outside the square root get multiplied together. Numbers inside the square root get multiplied together and simplified. So here we have 2 times 4 is 8 times the square root of 25 from our 5 times 5. And that just becomes 8 times 5, which is 40. Here we're going to have 3 square root of 7 times 2 square root of 3, and 3 square root of 7 times 3 square root of 5. So that gives me 6 square root of 21 minus 9 square root of 35. And we know that 7 times 3 is 21. There are no pairs there, so we can't break down square root of 21 anymore. And 35 is 7 times 5. Those are both prime, and no pairs there. So our final answer for this is just 6 square root of 21 minus 9 square root of 5. Now we want to talk about the quadratic formula. If we use the technique completing the square on the general quadratic equation ax squared plus bx plus c equals 0, we get any solution for a quadratic equation. And that's x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And there's a little song we'll learn about it in class to help remember it. So if the parabola crosses the x-axis, we're going to get two real solutions for x. If the parabola touches the x-axis, we get one real repeated solution. Remember, this will look like something like x minus 3 squared, and because this exponent is even, it will only touch versus cross the x-axis, and we learned this in the last chapter. If the parabola does not touch or cross the x-axis in any way, we have two complex solutions, which we'll cover later in this chapter. So, when we want to solve an equation with this quadratic formula, it's very easy. We have a general equation, ax squared plus bx plus c equals 0. And we have the equation that we want to solve. And we have to identify what a, b, and c are before we can proceed with the quadratic formula. So, if we look at our equation, the number out in front of x squared is always going to be 3. So a is 3. The number in front of our x term is b. So for us, this b is positive 7. And the number with no other, our constant, our c, is going to be c, so that's negative 1. Now we have all of these three things that we need to be able to plug into our quadratic formula. So we know that x is going to equal the negative of b, which is 7, plus or minus the square root of 7 squared, which is b, minus 4 times our a value, which is 3, times our c value, which is negative 1, all over 2 times our a value, which is 3. This looks like a mess, but we'll clean it up pretty soon. So negative 7 plus or minus, let's tackle what's under the square root. 7 squared is 49. Negative 4 times 3 times negative 1 is positive 12, and that's over 2 times 3, which is 6. Well, 49 plus 12 is 61, so that's negative 7 plus or minus the square root of 61 over 6. And that really can't be reduced any because 61 is prime. So, those are our two solutions. Now, they're not nice, they're not pretty, but they're solutions, and those are the exact numbers where this parabola crosses the x-axis. Here we have another one, and remember, x equals negative b plus or minus square root of b squared minus 4 times a times c over 2a. So, a in this case is negative 2. B is positive 5, C is negative 1. So the negative of B will be negative 5 plus or minus the square root of 5 squared minus 4 times A, which is negative 2, times C, which is negative 1, all over 2 times A, which is negative 2. So that's negative 5 plus or minus the square root of 25 minus negative 4 times negative 2 is positive 8, times another negative 1 is a negative 8, so minus 8 over negative 4. So here we have negative 5 plus or minus the square root of 17 over negative 4. So that's 5 plus or minus the square root of 17 over 4. Again, not pretty. 17 is prime though, so we can't simplify it. Steps to solving quadratics. Identify your a, b, and c. Substitute them into the equation. Solve for x. Simplify any radicals completely, and then simplify the solutions completely. This means eliminate the radicals when you can, and if you get something like 3 plus or minus 2, make sure you break it into two separate solutions like 1 and 5. Okay, determining types of solutions in advance. This is an interesting concept. What is under the radical tells you what type of solutions you will have. The stuff under the radical b squared minus 4ac is called the discriminant because it helps you discriminate what types of solutions you'll have. If the stuff under the radical is greater than 0, then you have 2 real solutions, and there may still be radicals involved. If the stuff under the radical is equal to 0, then you have 1 real repeated solution. This is where the parabola just touches the x-axis, but it does not cross. And then if b squared minus 4ac is less than 0, then you have 2 complex solutions. And this is where the parabola does not cross the x-axis. So graphically, what this looks like is you might have a parabola that crosses the x-axis like this. You might have a parabola that just reaches out and touches the x-axis. Or you might have a parabola that never touches any axis except the y-axis. Okay? So that would be what those 3 solutions, examples of what those 3 solutions look like. So let's look at these and figure out what types of solutions will be found for these quadratics. So a is 1, b is -4, c is 2, and remember we're looking at b squared minus 4ac. This is the stuff under the radical.